Hello students, this lecture will be discussing about the analysis of beams by using flexibility matrix method. So let us start with an example of a beam. In this example, this is a case of a continuous beam having one end fixed and the other end as roller, and an intermediate support uh, at B, which is roller. So in this case, a 60 kilonewton point load is acting in the span AB, and a point load of 30 kilonewton is acting in the span BC. Distance from the end A of this 60 kilonewton load is 2 meters. The span AB measures 4 meters. The span BC measures 4 meter, and the distance of this 30 kilonewton point load from the support C is 2 meters. In this case, we have to analyze this continuous beam, but the thing which has been given over here is that support B and C are showing a settlement of 12 meters and 6 meters respectively. That means this support B and this support C is giving a displacement, settlement of 12 mm and 6 mm respectively. So by keeping these things in mind, we'll simply proceed as we have done the analysis for previous cases. So first of all, step number one will be that we will be uh, drawing a M upon EI diagram for this. Before that, we need to know that how many coordinates should be there. So in this case, if we see at this support, number of reaction will be 3. At this support, it will be 1. At this support, it will be 1. So total, it will be 5. 5 minus 3. That is equilibrium equations. That is equals to 2. So this is the number of equations. This is the degree of static indeterminacy in this case. This is a degree of static indeterminacy in this case. So at least 2 coordinates should be selected in order to analyze this equation. So we'll start. So here, so we have selected this B and C as 2 coordinates. Coordinate direction 1 will be B and coordinate number 2 will be C. So the second step is we will draw the moment diagram and proceed to its M upon EI diagram. So this figure shows the M upon EI diagram. It is like this. This diagram varies like this. This is a real beam. This is a real beam, and this is its conjugate beam. We know that in case of a conjugate beam, the fixed end becomes free. That's what happens over here. Also, the free end becomes fixed. So A has become free and C has become fixed. So this is the bending, M upon EI diagram for the particular beam. And here, in this case, uh, the total displacement in the coordinate direction 1 will be this equals to the moment at B dash, that is over here in the conjugate beam. This is by conjugate beam theorem. We already know it. So moment at B dash will be what? Moment at B dash will be due to the loading, that is due to this load. So due to this load, it will be like this. This will be simply the load of this triangle, or sorry, this trapezium. Load of this trapezium will act at here. So load of this trapezium multiplied by the perpendicular distance, then again load of this trapezium multiplied by the perpendicular distance will give the total moment at the B dash. So it can be formulated like this. That is 120 multiplied by 2 multiplied by 3 plus 1 upon 2. That is a triangle. This we have divided into simply we have what we have done over here. We have divided this trapezium into two parts. First is this triangle and the second is this rectangle. So this is the load of the rectangular portion, this one, and this is the load of the triangular portion, this one. This is the load of the triangular portion. Then multiplied by the distance and will give the moment about B dash. So similarly, we have calculated this multiplied by the distance. Then for this one, it will be 120. This is 120 upon EI multiplied by this. This is the for this, and for this one, it if the total height is 300, then this height is 120. So this height will become 180. So that is what written over here, 300 minus 120, that will be 180. Then the height of this load of this triangle will be half into base into height, that is half multiplied by base, that is 2 multiplied by height. Height is 300 minus 120. So this is how we can calculate the total load of this the whole loading, and with the help of the loading we can easily calculate the moment. So this is the whole equation and we'll solve it, and the value comes out to be 1520 upon EI. Then similarly for the second case, this is 1520 upon EI. The value of EI may be given in the question. Yes, it is given. That is value of EI is 20 multiplied by 10 to the power 12 Newton mm square. So we have just substituted the value over here and we get the final displacement coordinate due to the loading in the coordinate direction 1 to be 1520 divided by 2000, that is equals to minus 0.076 meters. Similarly, we'll calculate the displacement due to the loading in the coordinate direction 2, that is over here. So over here it will be simply moment at C dash, sorry, coordinate direction 2, sorry, just a second. Coordinate direction 2 will be moment over here, that is C dash. So moment over C dash can be calculated using all this loading, because all this load will act as a moment over here. So we can simply calculate the moment at C dash, and that will give the value of uh, displacement in the coordinate direction C. So that is a moment at C dash in the conjugate beam. This is similarly, this comes to be in the same way. Uh, this is the load of this triangle, this trapezium, and this triangle. So the total load will consist of this trapezium, this trapezium, and this triangle. Obviously, we can break this trapezium into a triangle and a rectangle. Similarly, we can break this trapezium into a triangle and a rectangle, and this is all obviously a triangle. So this is how we can calculate the total load of this diagram and simply get the moment by using all this equation. We have get the moment over here, that is equals to minus 4279.86 upon EI, and by substituting the value of EI, we get the final delta 2L is equals to minus 0.214 meters. Now the flexibility matrix uh, for calculating for getting the flexibility matrix, we have to apply the unit load in coordinate direction 1 as well as 2 and get the final displacement. So this is how we have applied a unit load of 1 kilonewton in coordinate direction 1, and this is the M upon EI diagram for the same. This will give the value of del 11, that is displacement in coordinate direction 1 due to the load applied in coordinate direction 1 only. So this is displacement in coordinate direction 1, when the load is applied in the coordinate direction 1. So this is the load. This is a load. This is applied over here. So when we have applied over here the load of 1 kilonewton over here in the coordinate direction 1, this is a coordinate. This was 1 and this was 2. These are the coordinate directions. This is coordinate number 1 and coordinate number 2. We have applied load over here and we are seeing that its impact on the same point that denotes delta 1 1. Then in this case, similarly, that is moment at b dash. So moment over here and moment over here will be due to this triangular loading. This height is 4 upon EI. So this is half multiplied by base. Base is 4. This is 4 meters. Height is 4 upon EI. So this is half multiplied by base multiplied by height, and this is the distance from the centroid. So centroid of this triangle will be over here somewhere, and this is the distance, and this distance will be 2 by 3 of its base, that is 4. So this is simply 8 upon 3. That is what written over here, 8 upon 3. Now this will give this value, that is 21.333 divided by EI. Similarly, what we have done now, we have to calculate delta 21, sorry, del 21. That means the load is still applied on the coordinate direction 1, but its impact is seen on coordinate direction 2. So this is again, this is moment over here. So moment over here will be due to this. See, the load will be same, that is half into base into height, but the only thing will change is this distance. So this distance will be this distance will be that is 8 upon 3 plus 4. This is what written over here, 8 upon 3 plus 4, and this is half into base into height. So this will give the value, that is 53.333 upon pi. So in the first case, we have applied this unit load in the coordinate direction 1. Now we have 2 coordinates. So now in the second step, we'll apply this unit load in the coordinate direction 2 as well, and we'll calculate the displacement coordinates. So in this case, we have applied a unit load in coordinate direction 2, and the M upon EI diagram for the same comes out to be like this. Again, this del 12 represents that the load is applied on coordinate direction 2 and its impact is seen on coordinate direction 1, that is over here. So in this case, the impact is seen over here. So we have to calculate displacement coordinate in this over here. So that will be is equals to the moment over here in B dash. So moment over here will be simply due to this loading, that is the load of this that can be divided into load of this portion, that is a triangular portion, and this rectangular portion, and the whole load will give the moment at this point. So we have to calculate moment at MB dash, that will be is equals to del 12. So load of this triangle is half into base. Base is 4 into height. Height is 4 upon EI. See, this height is 4 upon EI. So height over here will be 4 upon EI. And the rest of the height will also be 4 upon EI. So this is 4 upon EI multiplied by 8 by 3. 8 by 3 is the distance from its centroid to this point. This is the distance, that is 8 upon EI, plus the rectangular portion. The load of this rectangular portion is 4 upon EI, that is length into width. So length is this 4 and width is this 4 upon EI multiplied by centroid. Centroid is at the center and at a distance of 2 meters. So this will give the value of 553.333 upon EI. Now, we'll apply. We'll calculate the coordinate direction. The same load is applied on the coordinate direction 2, and the impact is also seen on coordinate direction 2 only. So again, the only thing changes is the load value. This whole thing will produce a moment over here, and that is consist of uh, this is a whole triangle. So it will be simply half into base. Sorry, base is 8 and height is 8 upon EI. That will give the value 170.667 upon EI. This is multiplied by obviously the distance. So this might be the distance from the centroid of this triangle, and this we know that this is 2 by 3 of base. Base is 8, so that is 16 upon 3. This is what written over here. This is how we can we have calculated all the four coordinates, displacement coordinates, and we can simply write our flexibility equation. So this is we have we'll substitute the value of these coordinates into over here in this matrix. Now we have the thing given the question was the final displacement. See, in the question it was given that the support B and C are showing a settlement of 12 mm and 6 mm. So it means that these supports are showing a settlement. So we can simply conclude that the final matrix, that is delta matrix, will give this two coordinates components, that is minus 0.012. That was in mm, so we have converted it to meters, and the minus sign simply shows the settlement is in the downward direction. Similarly for the support C as well, that is minus 0.006. So we'll substitute all these value into this flexibility equation like this. These all are the values of delta, simply delta 11, delta, sorry, del 11, del 12. This is del 21, and this is del 2. So we have substituted all the values that we have calculated in the previous slides, and this is how it can be substituted to this flexibility equation. Now this is F1 and F2. These are the final forces in the coordinate direction 1 and coordinate direction 2, and that is equals to this delta. This is minus 0.012, and this is minus 0.016, minus this is delta L. We have calculated. We have already calculated this. Over here, we have calculated delta 1L and delta 2L. These are the final displacement due to the load in coordinate direction 1 and coordinate direction 2. So we have substituted the value over here, and this will give the final forces in coordinate direction 1 and coordinate direction 2, that is F1 and F2. That so this thing goes to this side, and this will give the inverse of this, and we can simply calculate its inverse like this. That is simply That is by putting the value of EI value of EI. We know that it is 20,000. So 20,000 divided by we have already discussed the method to calculate the inverse, that is 21.333 multiplied by 170.667 minus this thing, that is 53.333 multiplied by 53.333, or we can simply say it's square. Then again, this is what will happen. This will change its position, and this will change the sign. So this diagonal will change the position, and this diagonal will change the sign. So this is what happens over here, multiplied by this thing. On solving this equation, it will give the final forces, that is F1 is equals to minus 4.28 and F2 is equals to 25.71. So we have already discussed that this minus sign says that the direction we have taken for F1, let us see, the direction for F1 was upward, and the direction for F2, F2 was also upward. So minus sign shows that the direction will not be upward, it will be downward on coordinate direction 1. Whereas for coordinate direction 2, the direction that we have chosen was okay. So this is the uh, final bending moment diagram for the beam. This is due to the uh, this is 60 and this is 30, and this is 111. This is due to 0.41, and this is 42.84, and the portion that is cutting the both the diagrams will be the final bending moment diagram for this beam. This will give the value of MB. MB is moment at B. So moment at B, MB is equals to 25.71 multiplied by 4 minus 30 multiplied by 2. This will be 42.84 kilonewton meter. Similarly, moment at A will be 25.71 multiplied by 8. See, this 25.71, this was the final force. So final force was 25.71 multiplied by 8 minus 30 multiplied by 6. This is 30 multiplied by 6. This is the distance 6. So it is 30 multiplied by 6 minus 4.28. 4.28 was uh, sorry, 25.71 was F2, and 4.21 was 28 was F1. So F1, that is minus 4.28 multiplied by 4 minus 60 multiplied by 2. This is 60 multiplied by 2, because we are calculating moment over here at A. This is A, this is B, this is A, and this is B. So this is how we can calculate, and we'll get the final bending moment diagram for this case. So this is the calculation of free moment at BC triangle for the portion for this portion 30. This is 30 multiplied by 4, that is 30 kilonewton meter. This is what we have written over here, and this is free moment at AB. Is also triangle value of 60 kilonewton, so it will be WL by 4, that is 60 kilonewton meter. So BMD is over here. This is how we have analyzed this continuous beam using flexibility matrix approach. So in the next lectures, we'll be doing some more questions about by using this method. So thank you, class.